Alright, let's continue. We are solving number 6. Number 6 is a logarithmic equation. On the left, we have 2 logarithms. On the right, we have 1 logarithm. All those 3 logarithms have the same base, 5. We have no other terms. We actually had a very similar problem earlier, right? So it's natural to think that we're going to condense the left-hand side. We're going to add up the 2 like basis logarithms by applying the product rule. We keep the base and multiply their antis, x minus 1 times x plus 4. Now let's look at the equation. Left-hand side, 1 single logarithm. Right-hand side, 1 single logarithm. They are the same. They equal to each other. And they have the same base, 5, 5. Shouldn't they have the same anti as well? We equate the 2 antis, x minus 1 times x plus 4 equals x minus 5. FOIL the left-hand side. We try force times force plus outside times outside plus inside times inside plus last times last. Fill in the blanks. First, x, outside, x4. Inside, -1, x. Last, -1, 4. Let's reorganize this expression. X times x, x squared. 4 times x, 4x. -1 times x, -x. -1 times 4, -4. Equals x minus 5. We can combine those 2 terms. 4x minus x, 3x. X squared plus 3x minus 4 equals x minus 5. We are solving this quadratic equation. We want to keep the right-hand side be 0. So all the terms are going to go on the left. I'm going to move x over. So we would have a negative x on the left. Move negative 5 over. We would have a positive 5. Copy x squared plus 3x minus 4 minus x plus 5. That's my transposition of terms. Combine like terms. The reason we put them together because we cannot combine. We cannot combine like terms if they are on different sides of the equation. Now they are together, we can combine them. X squared. 3x minus x, 2x. Negative 4 plus 5, positive 1. I need more space here. Oops. Okay, so let's solve this quadratic equation. On the left, the trinomial actually is a perfect square. It is x plus 1 to the power of 2. If a perfect square equals 0, the base must be 0. The base is x plus 1. X plus 1 equals 0 gives us x equals negative 1. Are we done? No, we are solving a logarithmic equation. Very, very important. When we are solving a logarithmic equation, we need to double check our result. Not double check, we need to check our result. Let me write the original equation. Logarithm with base 5, x minus 1, plus logarithm with base 5, x plus 4, equals logarithm with base 5 of x minus 5. So let's plug in. X equals negative 1. We would have LOG with base 5. Negative 1 minus 1. You know, you don't have to go further. you already see a contradiction. So if we plug in x equals -1, here, the anti becomes -2. Could the anti of a logarithm be negative? No, that's a contradiction, right? Anti-logarithm has to be positive. So this is not defined. Means x equals -1 is extraneous. This means get rid of it. The only proposed solution turns out to be an extraneous solution. So the original equation has no solution. Am I clear about that? Yeah, this is an example that you need to pay attention. How do you solve it? That's one thing. After you got the proposed solution, how do you check if the solution is an actual solution or not is another thing. In this case, -1 is extraneous. Let me explain how would we have extraneous solution for logarithmic equation? Because let's look at the original equation. Those anti must be positive. Anti-logarithm has to be positive. Okay, so x minus 1 has to be positive. X plus 4 has to be positive. X minus 5 has to be positive. Means we have restrictions on the variable x in the very beginning in the equation. However, when we try to solve for x, after we remove the logarithm, we also removed the restrictions. We solved x equals -1. That actually is the solution for the quadratic equation. They are not exactly equivalent. Okay, they are not exactly the equivalent because we have no restriction on this equation. However, we do have restrictions on the original logarithmic equation. That's the reason we might have extraneous solutions. If we are not careful, if we do not do the check, then we would end up with the wrong answer. Like this one, we have a proposed solution. Turns out the function or the original equation is not even well defined at x equals -1. So the solution is extraneous. The original equation has no solution. Let's move to example 2. Let me read the problem. Example 2, we are going to simplify the given functions. Write each function as a single term with a coefficient of 1 if possible. So basically, we are condensing the function. Let's see how do we do that. Example 2, number 1. What is 0.35? Is that 3/4? Yes or no? Yes. Yeah. So you don't have to rewrite that as 3/4. We can keep the decimal here. By the power rule, we are able to put the coefficient 0.75 on the shoulder of the anti right here. That's the power rule. Okay, let me write the power rule again. I think I have written it many times. So if you have a coefficient of the logarithm, you are able to put it back inside the anti on the shoulder of x. So that's what we just did earlier. Continue. Simplify the anti. We keep the base x. We have two exponents for the base x. The first exponent is 4. Second exponent is 0.75. By the power rule, for the exponents, you learn that from algebra 1, algebra 2. We're going to keep the base x and multiply 4 and 0.75. You have a calculator. Multiply 4 by 0.75, you have 3. So you end up with a natural logarithm of x to the power of 3 after you simplify this function. Number 2. The function is a subtraction of 2 logarithm. the first logarithm has a coefficient. So we are going to apply power rule to put a 4 back inside the anti. That gives us logarithm, common logarithm, x cubed and then to the power of 4th minus common logarithm x squared. By the power rule, 3 times 4, 12. So that is a common logarithm of x to the power of 12 minus common logarithm of x squared. Subtraction. Now we could apply the quotient rule to condense this expression as one single common logarithm by taking the quotient of the two antis. Be careful with the order. X to the power of 12 go on the top, x squared on the bottom. Simplify x to the power of 12 over x squared. We have x to the power of 10th. Number 3. Number 3, actually, you see one single logarithm. The logarithm has a coefficient 2. Base is 10. The anti of the logarithm is kind of complicated. Yeah, let me erase this part. Let's give it a moment. I want to erase this part. It just doesn't let me, for some reason. I'll just rewrite it here. 2 log with base 10, 7 log with base 9 of 3. So the anti of the logarithm is very complicated. What's going on? So the whole thing here, that's the anti, right? The whole thing here is the anti. So let me close it and restart it. So I will have to make part 4 for this section. Let me stop here.